Hello, folks. So, this is part 18 of learning Rust from scratch. So, the last chapter that we were looking at was chapter 3, the common programming concepts. Now, we are looking at chapter 4, understanding ownership. So, let's get started. So, understanding ownership. So, ownership is apparently Rust's most unique feature, and it's not there in other languages, and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So there is no garbage collector which takes care of collecting the garbage, collecting unused objects, unused spaces in the heap, and then deleting it off and or reusing that space or whatever. So it's important to understand how ownership works, right? So this is what enables Rust to make memory safety guarantees. So in this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. All right. So let's get started. So what is ownership? So ownership is a set of rules that govern how a Rust program manages memory. Okay. The set of rules. Okay, that govern, I mean, ownership in the sense we generally think of ownership as an English term, and it is an English term, and it means someone who has ownership, someone who owns something. So, a house ownership would mean the act of owning up a house and owning a house and having a house. In this case, it's a set of rules apparently that govern how a Rust program, software program, manages memory. So all programs have to manage the way manage. So all programs, like not just Rust programs, so all software programs have to manage the way they use a computer's memory while the program is running, right? So some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. So if you don't free the memory, it just keeps increasing, I think. So Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks, right? So it's a system of ownership with a set of rules that the compiler checks. If any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. It's a compile time check, and it's a compile time feature. So I think it does not slow down your program while it's running. So none of the features of this ownership will slow down the program. So because ownership is a new concept for many programmers, it does take some time to get used to. So the good news is that the more experienced you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. So when you understand ownership, you'll have a solid foundation for understanding the features that make. So you'll have a solid foundation when you understand ownership. You'll have a solid foundation for understanding the features that make Rust unique. So there are some features that make Rust unique, and once you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. So in this chapter, we'll learn ownership by working through some examples that focus on a very common data structure, strings. So I remember reading this long ago. Let's look at it again. So strings, so is a common data structure. So it's a data type or data structure. So the stack and the heap. Many programming languages don't require you to think about the stack and the heap very often. But in a systems programming language like Rust or something like C, C++, or Golang, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Like why you have to make certain decisions. So parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. So both the stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. So the stack stores values in the order it gets them, and it removes them values in the opposite order. So it's like a stack, 1, 2, 3, 4, and then when you remove it's 4, 3, 2, 1. So this is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. So adding data is called pushing onto the stack, and removing data is called popping off the stack. So this one is pretty usual and general and known to many people because they know the stack data structure. So all data stored in the stack must have a known fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. So if there is a data that has unknown size at compile time or a size that might change during, like, let's say based on user input or um, during the running that might change must be stored on the heap instead. So heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough and marks it as being in use and returns a pointer which is the address of that location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. So this is allocating on the heap, so allocations. So even in Golang, when you do benchmark tests, you can actually see the number of allocations. And per operation, I think number of allocations per operation, how much data, like how much uh, bytes are taken up per operation and what. So because the pointer to the heap is a known fixed size, pointer to the heap is a known fixed size, you can store the pointer on the stack. So um, pointer size is known. It's like a address, and the address size is always known and fixed. You can store the pointer on the stack, but when you want actual data, you must actually dereference the pointer. You must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you have been seated to find you. So pushing to the stack is faster than allocating on the heap. So because allocator never has to search for a place to store new data. So in the case of stack, it's like in order it's put in, so it does not ever, like, the allocator does not ever have to search for a place. It does not ever have to search for a place. It never has to search for a place to store new data. So that location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because allocator must first find a big enough space to hold the data and then perform bookkeeping to prepare for the next allocation. It should remember how much space is held so that the bookkeeping so that you can prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the tables at one table before moving on to the next table. Taking an order from table A and then from table B and then from A again and then one from B again would be a much slower process. By the same token, a processor can do its job better if it works on the data that is close to other data, as it is on the stack. So rather than farther away as it can be on the heap. So the data on stack is pretty close by, so it works better. The processor can do its job better. So when your code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack. So when a function is called, the arguments or the parameters passed into the function and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. So once you understand ownership, you won't need to think about the stack and heap very often, but knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. So ownership rules. First, let's take a look at the ownership rules. Keep these rules in mind as we walk through the examples that illustrate them. Each value in Rust has an owner. There can only be one owner at a time. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So every value has an owner, and there can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So variable scope. Now that we have passed basic Rust syntax, we won't include all the function main. But we can see it. Um, Code and examples. So if you're following along, make sure to put the following examples inside a main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. As a first example of ownership, we will look at the scope of some variables. A scope is the range within a program for which an item is valid and available. Take the following variable. The variable s refers to a string literal, where the value of string is hard-coded into the text of our program. The variable is still valid from the point at which it's declared until the end of the current scope. Shows a program with comments annotating where the variable s would be valid. So here it's not valid because it's still not yet defined, declared or defined. So it's valid from this point onward and forward. Do stuff with s. This curve is normal and s is no longer valid, right? So you can actually run this, copy this, and run it in the Rust playground. You can just say this, right? You can say print line s s s s. Okay, so let's actually look at it and see if it works. So not found in the scope. So line 2, so it's not found in scope. Okay. Cannot find value s in the scope. So line 4, okay. Makes sense. And line 5, line 6, it should be there. Line 9, again not found in scope. So let's run this and it should just show hello. Right. So the scope of the variable is clear. There are two important points in time here. When s comes into scope, it is valid. It remains valid until it goes out of scope. At this point, the relationship between scopes and when variables are valid is similar to that in other programming languages. Now we'll build on top of this understanding by introducing the string type. The string type, to illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section of chapter 3. The types covered previously are of a known size, like a slice or an array, basically an array. Slice, we didn't talk much, but basically an array is of fixed size only, no variable size, and then booleans, integers, floating point numbers, and um, yeah, all of these are of known size, right? So you have integers, floating point numbers, booleans, and arrays, right? So they can be stored on the stack because they're of known size and popped off the stack when their scope is over and can be quickly and trivially copied to make a new independent instance if another part of code needs to use the same value in a different scope. But if you want to look at data that is stored in the heap and explore how Rust knows when to clean up that data, and string type is a great example. We'll concentrate on the parts of string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in chapter 8. You've already seen string literals, where a string value is hard coded into a program, software program. So these are string literals. String literals are convenient, but they aren't suitable for every situation in which we may want to use text. One reason is that they're immutable. Another is that not every string value can be known um, when we write our code. For example, what if we want to take user input and store it? For those situations, Rust has a second string type called string. So this type manages data allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. So you can create a string from a string literal using the from function like so. The double colon operator allows us to namespace this particular from function under the string type rather than using some sort of name like string underscore from. We'll discuss this syntax more in the method syntax section of chapter 5. So this is for methods and namespacing and all. And when we talk about namespacing with modules and paths for referring to an item in the module tree. This kind of string can be mutated. So mutable s string s dot to string world will print hello world. What's the difference here? Why can string be mutated but literals cannot be mutated? The difference is in how these two types deal with memory and allocation. In the case of a string literal, we know the contents of compile time, so the text is hard-coded directly into the final executable. This is why string literals are fast and efficient, but these properties only come from the string literals immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size may change while running the program. With the string time, in order to support a mutable growable piece of text, we need to allocate an amount of memory on the unknown at compile time to hold the contents. This means the memory must be requested from the memory allocator at runtime. We need a way of returning this memory to the allocator when we are done with the string, right? So that the allocator can like reuse the memory already borrowed, right? Reuse replace the space, or delete the data while clearing up the space. So that first part is done by us when we call sign string from. Its implementation requests the memory it needs from the operating system. This is pretty much universal in programming languages. However, the second part is different. In languages, the garbage collector. The garbage collector keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages, our code is GC. It's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. If we forget, we'll waste memory. If we do it too early, we'll have an invalid variable. If we do it twice, that's a bug too. We need to pair exactly one allocate with exactly one free. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Here's a version of our scope example from the 4.1 using a string instead of a string literal. String colon colon from. There is a natural point at which we can return to memory a string needs to be allocated when s goes out of scope. So when a variable goes out of scope, Rust calls special function for us. This function is called drop, and it's where the author of string can put the code to return the memory. Rust calls drop automatically at the closing curly bracket. Yeah, at the end of an item's lifetime is sometimes called resource acquisition is initialization. So the drop function in Rust will be familiar to you if you have used request acquisition is initialization. So this pattern has a profound impact on the way Rust code is written, and it may seem simple right now, but the behavior of code can be unexpected in more complicated situations. Okay, when you want to have multiple variables, you use the data we have allocated on heap. When you want to have So when you want to have multiple variables use the data that you have allocated on heap, it's going to be complicated. So those are complicated situations. Let's explore some of those situations now. Variables and data interacting with move. So multiple variants can interact with the same data in different ways and process. Let's look at an example using an integer and listing photo. We can probably guess what this is doing. Bind the value 5 to x and then make a copy of the value in x and then bind it to it. We now have two variables x and y and both are equal. This is indeed what is happening because integers are simple values with a known and fixed size. And these two five values are pushed onto the stack. Now let's look at the string version. String from hello. This looks similar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2. But this isn't quite what happens. Take a look at figure 4.1. See what is happening to string under the covers. A string is made of three parts. So it's the pointer, length, the capacity, a pointer to the memory that holds the contents of the string, a length, and a capacity. This group of data is stored in a stack. On the right is the memory on the heap that holds the contents. So the length is how much memory in bytes the contents of the string are currently using. So the capacity is the total number of amount of memory in bytes that the string has received from the pool allocator. Difference between length and capacity is that it's the same when it's at full capacity but not in this context. So for now, memory matters but not in this context. So for now, it's fine to ignore the capacity. Okay. So when we assign S1 to S2, the string literal data is copied. Meaning we copy the pointer. This is the thing that we're copying. We're not copying this pointer, the length and capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. Otherwise, the data representation in memory looks like figure 4. The representation does not look like 4-3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation ST could be very expensive in terms of runtime performance if the data on the heap were large. So earlier we said that when a variable goes out of scope, Rust automatically calls a drop function and cleans up the heap memory for the variable. But figure shows both data pointers pointing to the same location. This is the problem when S1 and S2 go out of scope. They will both try to free the same memory. This is known as double free error and is one of the memory because we mentioned previously. So free memory tries can lead to a memory corruption. This can potentially lead to security vulnerabilities. To ensure memory safety, after the line S2 equal S1, the Rust consider S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 and after S2 is created. It won't work. Okay. Mhm. Let's try out S1. It should come unused variable S2. Okay. So it is unused variable S2. We haven't used S2. So help this as intention prefix it with the underscore. S1 move occurs because S1 has size string, which does not implement the copy trait. Let S2 equal S1. The value moved here. The value moved from here to here, so and it S2. The value borrowed after move. So basically, the value moves away from S1 to S2. That's what they try to see here. Tensional after the line, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. So I'm trying to use S1 after S2 scale, and after S2 scale, this will work. Okay. I think I'm sleepy, so I'm just gonna go ahead and stop here and then come back and read this. That's all I have for this video. I'll see you in the next one. Bye bye.